All right, so today we'll just kind of do a recap lecture of the modeling unit that we've done so far. So we'll look back at the DERs that we studied and basically come up with a unifying framework that captures the dynamics of most of them, not solar, but pretty much everything else. Before I do that, though, I just want to talk really quickly about the mid-semester evaluations. So about half the people in the class did those. Thank you very much if you did, because I've told you before, but I'm kind of making this class up as I go along. So getting feedback as we go hopefully will help me tune it up. So some of you said very kind things, very encouraging things. I really appreciate that. There was also a lot of constructive feedback, and a lot of it was around the homework. So I'll try to make some changes there, but I just want to share some notes that people had brought up about the class. So one is that, this is good because it's looking forward, so it's like feed forward rather than feedback, right? So hopefully I can change this before it becomes a problem. But somebody said that having more guidance and structure around the semester project would be helpful. And that's totally fair, right? We haven't really talked about that at all, other than me saying it's going to be half your grade and that's going to be the focus of the second half of the semester. So I'll think about how to provide some guidance for that. Basically, maybe we'll do like a whole day, which is mainly discussion. So I'll ask people to try to come in person if they can, or to join in real time on Zoom if they can't. And then we can break up into our teams and I can like circulate, and maybe Priya or Sean, our RTA, can also circulate and talk with people. What's their idea? What's their kind of plan? And I may put in place a check where basically you write a couple paragraph proposal for your team and say, this is what we plan on doing for the final project. And then I can kind of check and iterate with you guys a little bit if needed. But there wasn't much about the project. Most of it was about homework. So there were a couple points where people said basically you want more time for homeworks. And I totally recognize that. I was hoping to stick to kind of a every Thursday homework deadline thing, but I was just getting way behind on making the homeworks. So I was like putting them up too late and not giving you guys enough time to work on them. So I think from now on, whenever I assign a homework, it'll just be due 1 week from the day that it's posted, basically. And I realize that's not super convenient for you. You might like to know, like, be able to structure your deadlines and stuff like that. So I apologize, but hopefully, the homeworks aren't super long. So hopefully a week gives you enough flexibility to find some good time to work on it. There was one comment about homework solutions, which the policy so far is that we're not posting solutions. We give you your grades. Those are visible in Gradescope, right? Has anybody been able to check their grades on Gradescope? Okay, cool, good. So you can see like, oh, I got everything right, or I got a few things wrong. And you can see in each question what you might have gotten wrong. But beyond that, like, we don't show you a full clean solution. And I'm going to be totally honest with you. The reason for that is that it's just basically about trying to make a good use of my time. So I plan to teach this class a bunch of times, and the more sort of information about solutions that I release, the more likely it will be that people in future semesters can just get those solutions. And that's fine. I don't mind. Like, I don't consider that cheating. I don't, I've told you guys you can use whatever resources you want for homework, basically, as long as you cite your sources. But I do think that the value of the homework is doing it without a solution in front of you, right? It's struggling with it, figuring out what you don't understand, and then, figuring out a way to remedy that misunderstanding, either through conversations with a TA or a friend or whatever. So in some sense, if I put a bunch of solutions up and they become widely available, then it kind of steals that opportunity from people. And maybe that's fine, right? And maybe I can trust people to just not look at the solutions, like try homework before they look at the solutions. You guys are grad students, you're mature. So maybe we'll do that. I'm not sure. But I do want to say that that I have solutions and Priya Darshan has solutions. So, and we have office hours covering 3 days of the week. So if you are confused about why you lost points on something, definitely I encourage you to come to office hours and we can talk it over. I think you're more likely to get, probably more out of that anyway than you would from just looking at like a cleanly written up PDF. So anyway, that's my take on that. But that policy may change. So if you feel strongly about it, feel free to talk to me or to Priya Darshan. Okay, and then beyond that, there were a bunch of comments like basically the homework is not super deep. The homework is not super informative. Sometimes it feels like I'm just giving you proofs to like fill your time this week. Okay, fair. So some of that, like, just again, to be totally honest, I'm making this up as I go along, and this is way more work than I thought it would be. So I sometimes get behind and I'm just like, oh, I got to give them something, right? So guilty is charged. I will try to do better about that. And so I think we'll aim for maybe a little bit less homework, but deeper homework. This week I tried to, and some people had mentioned this to me before outside of the survey forms, right? So I kind of realized this was an issue. So this week I tried to make it a little bit richer, a little bit more trying to convey understanding with the problems rather than just like get you guys to work through problems. So like the home heating, comparing gas heat and electric heat is, I think, one example of that. So anyway, that's something. And then yeah, some people ask for basically more coding, the feeling that some of the, like the GitHub repo that I post, I leave 3 lines empty and you guys can fill that in, but everything else, the other 100 lines and 3 subroutines or whatever are like just total black boxes and you have no idea where they're coming from, right? So I think, and I tried to do this early on, but I just kind of got out of the habit of it. But I think I will try to like open up MATLAB more in lecture and demo scripts for you guys, maybe open up some of those other subroutines and show you what they're doing. Not to the point where you necessarily could reproduce it, but to the point where you understand roughly, what you're going for. So, okay, I will stop there. Does anybody have comments or thoughts about that? Yep.
Yeah, I think so far, like the lectures have been really awesome, very informative. Like you explain things very well.
Oh, thank you.
Which is really nice. But then, yeah, I think on the homework, like it might be interesting to have like potentially, like in a future semester, do like a 2-week open thing, but then like a little bit of like a longer problem set.
Yeah.
I just as like a suggestion. I'm not sure if that'll like change formatting too much or not.
Yeah, no, that's a good suggestion. I'll just repeat that for folks on Zoom. So the suggestion basically was maybe every 2 weeks a homework set, but have it be longer and kind of deeper. And yeah, no, point taken. I think probably next year I'll try to do that. And we're getting to, my vision was that like basically before spring break we'd be doing problem sets, and after spring break you'd be doing maybe the occasional problem set, but mostly working on projects. That's kind of still what I'm hoping to stick to. So in some sense, like, this stuff is more relevant for next time I teach this class than it is for this time. But we'll probably still have 1 or 2 more, problem sets before we get to the midterm. So maybe I can experiment with that format a little more. Yeah, thank you. The other, yeah, please.
Yeah, I agree. I think the idea of having homeworks in the first part of the semester and then completely focusing on the project, it makes way more sense because I feel like it gets too hectic when I have a project report and homework due every week. So it gets too much. And when I say project report, I mean the intermediate, whatever. So I think that still makes sense, but yeah, maybe just fixing the structure.
Yeah, just to repeat that. So, and correct me if I'm wrong, but basically you like the structure of having kind of the homeworks front loaded into the first half so that you don't have to worry about both homework and project in the second half. Yeah. And then you said fixing that structure. Is that what you said at the end there?
Yeah.
Okay.
Yeah.
Oh, okay. I see. Yeah.
So maybe get, like Aaron said, that just
Deeper. Okay. Yeah. Yeah. I mean, okay, look, to be fair, if I had to think, how many hours have I spent on this? I don't want to count the number, but the percent that I've spent on lectures is probably like 90 to 95. And the percent that I spent making homeworks is like 5 to 10, right? So it's understandable, I guess, that the homework is of worse quality. So I'll try to tip that balance a little bit. Thank you. Yes.
It's not really a feedback, but I think there was a mid-semester exam that was spent.
Yeah.
I just want to know how it's going to be when.
Yeah. So how and when will the mid-semester exam be like? There will be one midterm, it'll be the only exam, and it's 30% of the grade, homework is 20, and the project is 50. So you will have it, I'm not sure, either it'll be the week before spring break, or it'll be probably not right after spring break, but maybe the following week. It seems a little cruel to give you guys a midterm right after break. But the following week, I think, is fair game. So depending on how quickly I can prepare it, it'll either be the week before spring break or 2 weeks after. And then it'll be a 24-hour take-home exam. And so I'll post it online, and then you start the clock basically, and then you find some time hopefully to work on it. We can discuss when that would be good. Like, do people, let's see, who would prefer that to be on a weekend? So the 24-hour take-home on a weekend. So I see 4, and then who would prefer it to be during the week? Yeah, 7. Okay, so that's a soft majority, I guess, of voters, and that's a pretty big majority of voters for the week. So we'll probably do that. And then is there a good day for people? This is going to be impossible to find a day that's good for everybody, but let me just do a show of hands. Who thinks Monday is their favorite day to have a take home final exam? One Monday, okay, Tuesday, Wednesday, Thursday. Oh, there's a lot of votes for Thursday. Okay, Friday. What? You want Friday? You guys want Friday?
Yeah, I was
Okay.
gonna say, like Sunday night till Sunday 10 p.m. till Monday 10 p.m. to give everybody, not 10 p.m. like whatever. time.
Yeah, that's fair. Then you could work a little bit on Sunday night if you wanted.
Yeah.
Okay, all right. Let's tell you. Well, let's take this offline. We can talk about it on Discord or something like that, and then we'll figure it out. But yeah, thank you for the suggestions. Yes.
The code that you have for the homework problems, is that code that you come up with in the course of your research, or you wrote it for the homework?
So the question is, the code that I post for the homework problems, is that code that I've used for research or stuff that I've created for this class? It's mostly stuff I've created for this class, but it definitely ties in very closely with things I've done in research. So it's not like I just like from scratch come up with everything, right? Yeah. I mean, in some sense, what I'm trying to do with this class is synthesize all the what I think are the coolest, best things that I've learned as a researcher for like a decade or whatever, and put them into one semester. So it's all stuff, mostly stuff that's pretty close to my research, not all of it. Yeah. Okay, well, thank you all for that. Yep.
So like the problem set for the homework, is it like something like similar to problems that set for the midterm exam, or are we expecting like different problems, or are we just expecting like problems will found like how we solve some questions and then filling codes, is that like the structure we should expect?
Yeah, so the question is, for the midterm exam, what structure should we expect? Will it be similar to a homework where you have, a couple of written questions and then fill in some lines of code, or will it be something else? I think, like, I haven't made it yet, so I don't know, but what I'm thinking is probably it will be a combination of like some written work and some coding work. And I think the written work will probably not be hopefully too hard or too long. The coding work might be a little bit more open-ended than what I've given you so far. So my thinking is that I might, basically ask you to think about a system that has multiple DERs in it. So I might say, for example, an EV and solar. And then I want you to, basically write down some equations that describe, how that combined system would evolve, its dynamics and stuff like that. And then once you have the equations, take them and program them. And so I might give you starter code. Probably I will give you some starter code, but probably less than what I give you for homework assignments. But the stuff that you've already done on homework assignments is fair game. So, if you've already written a function that can simulate an EV, you can basically copy and paste that in the midterm, right? So that's kind of my vague plan at this point. Does that make sense? Okay. Good. Well, thank you for that feedback. I really appreciate it. Any other questions before we get started with lecture? Okay. Yeah, so again, today, basically, it's going to be a look back at what we have done so far in the modeling unit, and then kind of coming up with a unified framework that we can use to think about most, not all, but most of the DERs that we've learned about so far. So we'll start with talking about batteries and EVs. That was our first, significant modeling lecture after we kind of got the ODE and dynamical systems material under our belts. We'll talk about passive thermal storage. So this is basically in indoor air and shallow thermal mass in buildings, and also in the deeper thermal mass. We'll talk about active thermal storage, which is basically the three types of thermal storage that we learned about in that lecture, lumped or well-mixed sensible, stratified sensible storage, and then latent storage. And then we'll come up with a unified model, basically generalize each component of each of the models that we look at and say, here are the equations that can describe basically anything that we've learned about so far, without solar, the exception of solar. And then I'll wrap up by just talking about some things that I consider DERs, but that we're not really going to talk about much this semester. But if you want to model or talk about these things in your projects, they're fair game, and we can certainly talk about that in office hours or something. Okay, so basically, I'm just gonna it's just gonna be a bunch of modeling stuff for like 15 slides here. So so bear with me. Okay, so for a stationary battery, we'll recall that the state, we're just calling it X. It's in units of energy, and that's just the chemical potential energy that's stored in molecules, inside the battery. And the action we can think of as the charging power. And then the output of the system we can think of as the electrical charging power. And so these things are positive if we're putting energy into the battery and negative if we're taking energy out of the battery. So batteries have energy capacities in general, an upper limit. Everyone has an upper limit, but some may have lower limits as well. So for example, a home battery might have a hard lower constraint on never discharging below, say, 40%. So that there's always enough energy in the battery to power a house in case of a power outage for a day or something. And then they have charging capacities as well that can be viewed as limits basically on the action U here, the chemical charging power. And so those are basically the electrical charging limits, either multiplied or divided by the efficiency of charging or discharging. And then batteries have time constants. Often for lithium-ion batteries, it's a reasonable assumption to take that self-dissipation time constant to be very large or even infinity. But for generality, we can leave it as finite. And then we get basically dynamics parameters that will show up in our battery model. So A is going to be the thing that multiplies the state in our discrete time dynamics model. And that's just e to the minus delta t on tau. You guys have done a bunch of homework on this now, so you know where that comes from. That should be very familiar. And then B is just 1 minus A times the time constant tau. So B has units of hours, and that'll be what multiplies basically the power term in the dynamics. And here's what that looks like. It just says the new energy at the next time step is A times the old energy plus B times the chemical power that we put in. And then we have our constraints, our upper and lower limit on both the state and the action. And then we have an output equation, which is not linear. So everything else in this model is linear. The output equation is piecewise linear. So there's a relationship between U, the chemical charging power, and P, the electrical charging power. And you can see it has this kind of piecewise linear form. And you can write that as the maximum of the discharge efficiency times U, which would be an orange line that would kind of extend like this, and the blue line here. So whenever that blue line is larger, that's the electric power. And then whenever the orange line is the larger one, that is the electric power. Okay, so this is all recap. Any questions about this? All right, cool. And then EVs basically are just like stationary batteries, but the constraints on the action are a little bit different because they're in fact time varying, and they depend on whether or not the car is plugged in. So if the car is unplugged, of course we can't charge or discharge. So we get 0 for both the lower and the upper limit on U. And then if it is plugged in, then basically the capacities end up being the same as they are in the stationary battery. But a lot of EVs, in fact, the vast majority of EVs today can only do one-way charging. So they can't discharge to power a house, for example. And so for those EVs, PD would just be equal to 0. And so we'd have 0 and then eta P on the high end. And then the model is just the same as it is for a stationary battery, except now we have time varying capacities or constraints on the charger. So if we look back, we'd have all the same equations, but there would just be a K here on the lower and the upper limits. All right, simple enough. So we talked about buildings, and we talked about basically the energy storage elements within buildings, essentially the shallow thermal mass that has to do with the air inside of rooms and the first couple of centimeters of walls and things like that. Ducts and other metal that is pretty fast to respond to changes in the air temperature. And then we talked about the deeper thermal mass. If you drilled into this wall, there's a bunch of cinder blocks in here, and if you got a foot deep, the temperature back there would be significantly different than the temperature in the room. More energy storage capacity, but sort of harder to access. Okay, so we came up with battery models for both of those. And I'm putting them in kind of this general framework here where we have a state X and action U. And then the output is the electric power P. And for the indoor air, and what you might call the shallow thermal mass, the capacitance, the energy is defined as the thermal capacitance. So this thing has units of kilowatt hours per degree, times the difference between the actual temperature T and then some baseline temperature, T hat, or nominal temperature. And so the hats here, you may remember, denote basically normal operation. So it's really by adjusting the building away from its kind of normal operating state that we can store or charge or discharge the thermal mass. And the action then is essentially the perturbation, the adjustment that we make to the thermal power that we inject, or if it's negative, that we extract from the indoor air. And then the output P is just the thermal power divided by the COP of the heating or cooling equipment. And our thermal capacities, so we assume that the actual measured temperature T that we experience, that there are kind of comfortable limits, upper and lower limits on that. So we'd say that our battery is fully discharged. It's at its lower limit when the indoor temperature reaches T min here, T underline. And then, similarly, we're at the maximum capacity. We've put as much energy as we can comfortably put into the indoor air once the temperature reaches this T max. So you just take the energy definition up here and plug in the max and the min limits. And then similarly, the equipment is going to have capacity limits, which in general can be a function of time. So we basically define the upper and lower limits on the perturbation, the adjustment, in terms of the baseline Q hat, and then the Q max and Q min for the equipment. And then we can define a time constant having to do with the self dissipation of the virtual battery that is the thermal mass, and that's R. So this is the overall thermal resistance connecting the indoor air to the boundary temperature, which can just be the outdoor temperature, or as we talked about, it can be kind of a mixture between the outdoor temperature and the temperatures of the adjacent spaces. So it's R times C, where C is the thermal capacitance of the air and the other shallow mass. And then the dynamics parameters are defined exactly the same way as they were for the battery models. And here, A, for a battery might be like 0.999, but A for the shallow thermal mass in a building might be like 0.8, 0.85. So when we look at the equation here, it's basically saying 85% or something like that of the energy is retained from one time step to the next. And that depends, that's for like hourly time steps maybe. So that's more or less saying that like 15% of the stored energy is going to dissipate effectively. So if I raise the temperature in the room by a couple of degrees, and then I let it just kind of do its thing for an hour or two, some of that stored energy is going to dissipate to outside or to adjacent spaces. Okay, but we still get the same model that the new X is A times the old X plus B times U. And the constraints look the same, except now they're both time varying. And the output equation here is just that the power, the true power that we would measure, with a power meter on the equipment, is equal to the baseline power P hat plus the perturbation of the thermal power divided by the COP. So what that might look like if we plotted power versus time, you can think of this as being like maybe a day. And I guess this could be a hot day where we're doing air conditioning, say. And maybe this is the night period where the demand is low. And then this is the afternoon here where it's hottest outside and the demand is hottest. So our baseline power might be this kind of P hat thing. And then we perturb, by taking some action, we heat more or less than we normally would have. So we do this kind of perturbation thing. And if we add the two of those, we get the actual measured power that we're putting into the building. And so it's really those perturbations, those wiggles that we use in order to sort of store energy or discharge energy from the thermal mass. Does that make sense? Okay. All right, and then the deeper thermal mass. So again, we define the state similarly. It's just the thermal capacitance in units of energy per temperature times the temperature difference between kind of the mass temperature as it is, as we would measure it, minus the thermal mass temperature as it would be in kind of a baseline operating scenario. And then the action here has units of power, but it's actually the actual temperature measured in the space, or the air temperature in the space, minus what that air temperature would be in baseline operation. So basically, if I want to, store energy in the thermal mass in this wall, I need to warm up the indoor air and keep it warm for a while, so that heat will bleed from the air basically into that deeper mass. And so dividing by R basically puts this temperature into units of power, because R will have units of temperature divided by power. And then the output looks just the same as it did in the previous shallow thermal mass model. And the energy capacities look the same as well. They just have to do with, we specify some, hottest or coldest temperatures that are kind of comfortable for the thermal mass. And then we subtract off the baseline, the T hat. And the power capacity is the same thing. We just assume there's only, so high that we can raise the temperature in the room before it makes people uncomfortable, or so low that we can drop it before people start getting cold. And so that effectively defines, the power that we can put in to the deep thermal mass. And then we have a time constant, RC, same as it was for the previous model. And again, the dynamics parameters have the exact same definitions. So the model ends up being just the same as it was for the indoor air, but now the output equation looks a little bit different. So we still have the actual, measured electric power on the left-hand side, but on the right-hand side, we still have the power under kind of normal baseline operations. But then we have this weird looking term here. So we still have 1 over COP, but rather than just having a thermal power perturbation, we have this other kind of weird looking thing in here. So we have a scaled version of U, and then we have X, but divided by the time constant. So it's a little weird. And by the way, this is not something that I talked about in the lecture on buildings, or 2 lectures on buildings. So I'll just show briefly where this equation comes from. But before I do, I think the interesting characteristic of this equation is it actually depends on the state. So now the power that we get, the power perturbation that we get, actually depends on how much energy we currently have stored in the walls, which wasn't the case for any of the previous models. All right, so where does that come from? Well, you may remember we came up with these battery models for buildings by doing kind of a 2-timing approximation. So we said, well, there's kind of 2 characteristic timescales, a fast one associated with the sort of light or shallow thermal mass, and then a slow timescale associated with this kind of heavier, deeper thermal mass. And we kind of made 2 different assumptions that led to basically a fast battery for the shallow thermal mass, and then a slower battery for the deeper thermal mass. And in that second one, we took our 2R, 2C model, and we basically assumed that at the timescales, the slower timescales of the thermal mass, that the air temperature responded essentially instantaneously to changes in the boundary conditions. So its derivative then is essentially always equal to 0. This is what's called the quasi-steady state model. So then we can take the 2R, 2C model and basically solve it for QC, and we get this equation here. So you can imagine if you rearrange this equation that it would look like that 2R, 2C differential equation, where you'd have C times a T dot, a rate of change of temperature on one side, and then you'd have these kind of delta T over R and Q terms on the other side. Okay, so this is true in kind of the measure, the actual temperature and the actual power, but it would also be true under kind of a baseline operation scenario. We still would have the dynamics and the output equations satisfied by those things. So here the hats, they satisfy these same equations basically. And then if we take the difference between those two, and I probably should have rolled this out in stages, sorry, this is a lot. Then we have on the right-hand side, so if you take equation 1 and subtract equation 2 here, then you can see, let me just hide that for a sec. You can see that the things that don't have hats on them, which is the outdoor temperature, well, that's the same, whether we're in baseline scenario or kind of in an actual perturbed scenario. So the T for the outdoor temperature is the same regardless. So when we take the difference of these equations, you can see that those are going to drop out. And then the QE, the exogenous thermal power, this is again body heat and heat coming from electronics and sunlight and stuff like that. That's the same no matter really what we're doing with the HVAC equipment. So so those will basically drop out as well when we take the difference. Okay, so then you can see we've got a T minus a T hat term divided by RM, And that's what this R is from. And then we'll have another term here where we have a T minus T hat divided by R out for the outdoor temperature. And so that's where the R out is coming from. And then we also have a Tm minus Tm hat divided by Rm. So that's where this term here is coming from. So in the second line, we just notice that T minus T hat, well, that basically is the action U, the perturbation in the indoor temperature that we're making. But we multiply by R because the definition of U here was delta T divided by R. So when we solve for delta T, we'll have a U times R on the left-hand side there. Okay, so that's where this term comes from. And then T minus T hat, well, that's just equal to X, the stored energy, divided by the thermal capacitance. So now we get an RC in the denominator there. And that is what we're calling the time constant associated with the thermal mass. And then the Rm went away. Basically, we just take this thing in parentheses and multiply through everywhere by Rm. So we get a 1 from this term and then a ratio of R's from the other term. And that, if we look back at the output equation, is the same thing that shows up in here. So that is the thermal power perturbation. And then we take the thermal power perturbation divided by the COP, and that gives us an electric power perturbation. So does that kind of make sense? Okay, cool. All right, so that gives us batteries and EVs. It gives us the thermal mass of buildings and the HVAC equipment that serves them. And then we can do active thermal storage as well. And we talked in that lecture on thermal storage and water heaters about how these things can be viewed kind of as thermal batteries. So I'm just kind of recapping that here. So for the simplest model is the lumped or the well-mixed thermal storage. And there we define the stored energy very similarly. It's just C times a delta T, where this thing TLS, LS stands for lumped sensible. And this is like a benchmark or a baseline temperature that we specify. Sort of like when you're talking about potential energy, gravitational potential energy in a mechanics class, you always define, what is the height or the elevation at which your potential is defined to be 0. So we're doing the same thing here. Basically, TLS is just the temperature at which we define the energy in the tank to be 0. And then the action, rather than being a perturbation, it's just the amount of power that we're putting in. So this looks more like the battery model that we saw initially. And then the output is just the power that we're getting out, or sorry, the electric power that we're putting in. And the capacities, again, they basically come from safe or comfortable limits on the amount of the temperature of the stuff in storage. So we get a C times T min minus our base temperature, and then similarly on the upper limit. And the thermal power capacities just come directly from the limits of the HVAC equipment that serves the storage, that charges or discharges the storage. We have a time constant. Again, this is just RC. The A and the B parameters are defined kind of the same as they ever were. But now we have a disturbance in the dynamics. So rather than just having an AX plus BU, we also have a W in the dynamics equation. And you can look up the derivation of where this came from in the thermal storage slides if you want. But it has to do with basically the QD. So this is what's being withdrawn by sort of uncontrolled stuff from the tank. So if we're talking about a water heater, this is basically people taking showers, pulling energy out of the tank. All right, so the dynamics now look slightly different. So we still have the X nu is equal to the old X times A plus B times U, but now we also have a disturbance term W in the dynamics here. And then we have our capacity constraints, which in general can be time varying. And our power equation in this case is much simpler. It's just a linear relationship. So the stratified thermal storage model. So again, here the idea was that rather than having whole tanks, say, of water that was all at the same temperature, we have kind of a hot column of water sitting on top of a cold column of water, and with a thermocline, a region where there's a steep temperature change in between those two layers. And so there, the state definition. Oops, this is a typo. This should be Y, not P. And what Y is, it basically is the a dimensionless version of the height of the thermocline. So when the thermocline is all the way at the bottom, then the tank is fully charged. When the thermocline goes all the way to the top, then the tank is empty, essentially. Right, so it would be y times some delta t, and then again, we have this sort of benchmark or base temperature, I guess. And here SS just stands for stratified sensible. And then thermal capacities defined quite similarly. And the power capacities again are the same. And the time constant ends up being the same. The parameters are the same. And the disturbance looks very similar, but with a slight change that we have potentially a different benchmark temperature there. And the model is the same as well. It's just we have time invariant energy capacities for this one. And then for the latent thermal storage model, so again, this one, the idea was that we have some phase change material that's undergoing some phase change as we charge it or discharge it. And typically it's between liquid and solid phases, but I guess you could do other phases as well. And so the energy stored in the tank we defined as Tm, so this is the melting point temperature of the material, minus TL, where this is again a benchmark kind of temperature at which we define the energy in the tank to be 0. So the idea is that maybe you start at this TL and then you put energy in to sort of raise the temperature of the fluid in the tank. And then, sorry, of maybe the solid in the tank rather, and then you reach the melting point and it begins to turn to liquid. And so here ML is the mass of liquid stored in the tank. And then U, this is the thermal charging power, and P is the electric power associated with that. And the capacity constraints, basically when ML is equal to 0, that means there's no liquid mass, so all the mass is solid still. And so that gives us our lower energy limit. And then the upper energy limit is basically when ML, the mass of the liquid, melted mass in the tank, equals the total mass M in the tank. And then we have thermal power capacities, same as the previous models. And interestingly here, because phase changes happen at constant temperature, more or less, the state of the tank, basically how much mass is melted or solid, doesn't really influence the losses in the tank. So there is no self-dissipation time constant in this model, or rather the time constant goes to infinity. And that means that the dynamics parameters here, this is a typo and I will fix this, but A goes to 1 and B goes to delta T. And I'll show where that comes from in a sec. And again, we have a disturbance term in this model that looks pretty similar to the previous two. Okay, so these are the correct versions of A and B. So if you want, you can correct the previous slides. I'll put up a corrected version later today, probably. Okay, so where do these things come from? Well, it turns out that they can be viewed as just the limiting cases as the time constant goes to infinity of the parameters that we were using in all the previous models. So that's easy to see for A, right? So if we take e to the minus delta t on tau, well, delta t is a constant. And as tau goes to infinity, we're dividing by bigger and bigger stuff. So the argument of the exponential here goes to 0. And then e to the 0, well, that's 1. So that limit is easy to see. Does anyone remember L'Hopital's rule from calculus? Does anyone want to say what L'Hopital's rule is? You guys raise your hand, so now you're on the spot. Yeah. So the limit is the same as the limit of its derivative, basically. And L'Hopital's rule specifically applies when you have the ratio of two functions. So you have like an f over g. So the limit of f over g is the same as the limit of f prime over g prime, under some assumptions about continuity and stuff like that. But yeah, very, very good. Okay, so if we take the limit of b, 1 minus a times tau, as tau goes to infinity, well, you can see this limit is not as straightforward, right? Because we have one thing that's going to infinity, the tau, but then we have another thing that's going to, well, I guess in this case, going to 0, because this thing is going to 1, and 1 minus 1, well, that's 0. So we have this like fight. We have one thing getting big and one thing getting small, and we don't know what wins. So let's see who wins here. So basically the key to finding this limit is just to write it as a ratio and then apply L'Hopital's rule. So to do that, we divide basically, or write tau as, 1/alpha. And then we have a ratio of two things here. And the limit, so we define alpha as 1/tau. So as tau goes to infinity, well, that just means that alpha is going to 0. Right? 1/infinity is 0. So now we take the derivative. This is the L'Hopital step. So we have the derivative on top and the derivative on the bottom. And the bottom derivative, well, that's pretty simple. That's just 1. And the top derivative is not too bad either. This term is going to vanish, and then we just have the derivative of an exponential. So we get a delta t, a negative delta t coming down, and then we have a negative sign here as well, so that becomes a positive delta t multiplying the exponential. And now the delta t can factor out, and we're just left with this limit again, which is the same as the limit that we had up. Oh, not quite the same, but it's similar to the limit that we had up there. So now alpha goes to 0, and e to the 0 is 1, and so we just get delta t. So although the latent model looks kind of different from the other models, you can view it as a limiting case of them. And in fact, the lithium-ion models, often the time constant is like really, really long. It's like thousands of hours. And so a pretty good approximation is 1,000 equals infinity, right? And then that gets you back basically to this model here, with the A is 1 and B is delta t. Okay, and then the model here for latent thermal storage is just the same as it was for the stratified model. So nothing new there. So that covers basically everything that we talked about in this modeling section, except for solar, right? Solar is not a battery. It's an energy source. It's not something we store energy in. But other than solar, this basically captures everything that we've talked about so far. So let's just like stare at all those equations and think about it and see if we can write down a general model that we could specialize in certain ways to capture any of the cases that we've thought about so far. And that's kind of easy to do. You could just be like, the dynamics are some function, and then there's some output equation, and they have some form, right? That's a general model, but we sort of want the simplest version of a general model that captures all these. And so it turns out that it has this dynamic form, which is just ax plus bu with a w in there as well. And for some of the models, w is 0. Okay, well, that's a simple specialization of this general model that gets us to, say, the battery model. And the dynamics here are time invariant. All that means is that these parameters a and b do not depend on time. They're just constants. And then we have, these are called box constraints on the state. And then, we have a lower limit and upper limit that can, in general, both depend on time. Of course, if you have a constant, that's fine. It's just a special case of a time varying thing where the thing happens to be constant. And then the constraints on u, the action are similar. And then the output equation kind of has this interesting form. So we need a time dependence in that equation because a lot of the equations had something like a COP, which is a time varying parameter, or they had like a p hat, a baseline power consumption, which can vary over time as well. So we need a time argument in there. And then one of the models, the deep thermal mass model, had state dependence as well. So we need an x in here, and then a u. And rather than having a linear function, we actually need nonlinearity there because a couple of them had sort of piecewise linear definitions. So this is in general a nonlinear, time varying, state dependent output equation, but the nonlinearity is pretty mild. It's basically piecewise linear, captures everything that we need. And that's it. So, okay, so why did I do this? So as we wrap up the modeling unit, we're going to start an optimization unit, which is going to be about how do we design and size and operate DERs effectively. So we'll go back to kind of eating our vegetables, right? We'll learn about some more math and algorithm kind of stuff and learning software tools. We'll use a package in MATLAB called CVX, which is stands for convex. So it's used for convex optimization. And we'll learn a little bit of theory and stuff like that. It allows us basically to be good users of that software. But the basic idea, the motivation for doing this kind of unified model is that, hey, this is a fairly simple model. It's a bunch of linear equations or linear inequalities. And then this function here, g, even in the nonlinear case, it turns out will have pretty good structure for optimization. It'll end up being convex and piecewise linear and things like that that we can take advantage of. So the idea then is basically the big DERs that we care about in this class, the things that use a lot of energy and a lot of power, we can all cast in this modeling framework. So now if we can come up with optimization and control methods that work for systems like this, then in some sense we've won, right? We've built muscles that we can use to, I don't know where I'm going with that. We've developed tools that we can use to fix and create and build a whole bunch of interesting stuff. Okay, does that make sense why we're doing this? Maybe I should have led with that. But anyway, okay, so just going to talk about this again as a summary here. So basically for all of the models, we had this definition of A and B that show up in the dynamics. The only difference was in the latent model for thermal storage, we had A as 1 and B as delta T, but we can view that as just a limiting case as tau goes to infinity of the same formulas. So basically, this is where I say everything is kind of a battery. This is essentially a battery model. And the disturbance ended up being 0 for a bunch of the models. I think we had 7 total models, and for 4 of the 7, there was no W in the dynamics. However, when doing control design, we might still want to put a W in there. The idea is that disturbance terms in control design often model, there's sort of a catch-all for all sorts of stuff. It could be, you got a parameter wrong when you're doing modeling, you use 0.87 and in reality it was 0.88 or something. And so that causes some changes to the behavior that you're not expecting. Or we just recognize like, hey, a battery is a complicated chemical and electrical device. It's got all sorts of weird stuff going on the inside. In reality, it can't actually be captured with this simple kind of one-state linear equation. But the bulk of the dynamics, most of the important behavior we can capture with that simple equation. So we use it, and then we throw in some kind of random disturbance to say, we want to be robust to model inaccuracies, basically. And so anyway, we might want to come up with basically a fictitious disturbance to use in our modeling for these things anyway. And then it had a non-zero interpretation for the thermal storage things, having to do basically with people pulling energy out of the thermal storage. The load that's being served by the thermal storage, whether it's water for hot showers or cooling for a building, something like that. And then the state constraints, okay, it's not that interesting. They all look basically the same. It's just some of them, the limits change over time and some of them stay constant. And it's about half and half there, the breakdown. And the action constraints, interestingly, are only time invariant for the very simplest model, the stationary battery. As soon as you just let the battery move around, where it's unplugged sometimes and sometimes not, then the constraints become time varying. And everything else is time varying in the action constraints. And then the output equation. So this is what basically gives us the electric power as a function of what's happening with the battery or the building or the thermal storage or whatever. So this thing ends up being a nonlinear function and not too bad of nonlinearities. Again, just piecewise linear, and time invariant and state independent. So there's no X that shows up in the equation. Time invariant just means that the parameters in the battery, the efficiencies and the capacities, that those things don't change over time. Of course, in reality, they might, right? We might want to use a time varying model there anyway, because for example, my bike battery, as it gets older and older, or when it's colder and colder outside, its ability to discharge quickly to get me up a hill or whatever gets worse, right? A laptop battery, its energy capacity decreases over time. We have all observed that. So you might still want to use a time varying model up here. And then for the others, actually there are 7, so for 4 of the others, we get a linear model, really an affine model, and it's linear plus an offset, but linear and it's time varying because some of the coefficients, like the coefficient of performance of a heating system, a heat pump, or an air conditioner might vary with the outdoor temperature. And then it's state independent, so no X shows up in there. And then we had this one oddball that did have the state dependence, and that was the deeper thermal mass model. All right, so that's all really, and then I'm just going to talk about a few things, just mention them briefly, that we haven't really discussed, but that other people might consider DERs. So if you want to be kind of, I don't know, have a wide vocabulary and be able to talk to other people in the area, it's good to at least be kind of aware of them. Right? So before I dig into that, any questions about the other stuff that we've done today?
These capture like the bulk dynamics, like you mentioned, but are there different like times or instances that like, the model kind of breaks down or you get some weird kind of edge cases? Like, does that happen every now and then?
Yeah.
I don't know, yeah.
For sure. So the question for other folks is, these equations capture like the basic, core of dynamics or something, but are there situations when they become inaccurate or they break down or they're, insufficient in some way? And the answer is yeah, absolutely. So one example would be, what if you have coupling between multiple of these things? So maybe I have a battery in the house and I'm charging it, and the heat that's being dissipated from that charging process basically enters into the air in, say, the basement, where in the DC house we saw in the tour last week that there was a big battery in the basement, right? So then that heat loss, okay, it's not useful energy that's going into chemical potential energy in the battery, but it is becoming heat that's going into the building. And so you'd have some coupling then through that heat transfer between the building model and the battery model. Similarly, with the water heater, we have these dissipative losses, heat bleeding out through the insulation in the walls. Well, where's that heat going? It's going to the building. So there'd be coupling between a water heater model and the building model as well. And then even within a building, you could have air and thermal mass, and you'd want to treat both of them as batteries. And naturally, there's some coupling there. And so it might make sense to use not two separate, one state models, but to use a genuine kind of two-state model there, like the 2R, 2C thermal circuit that we talked about. And so there you wouldn't have a simple, you would no longer have this dynamics equation, right? You would no longer just have a scalar system, you'd have a vector system with multiple states. And the dynamics might not look really that much like this anymore. So, yeah, and then just like life is nonlinear, right? So all this stuff is linear, but in reality, like, things are nonlinear. And so there are certainly limits in which, this linear approximation thing, these linear models are not so great. Yeah, but like what we're going to do in coming units is come up with things like control methods that use feedback and so forth. And the secret, the dirty secret of model-based control is that your model doesn't usually need to be very good in order to still give good controller performance, because we can use feedback, basically. So we'll talk about that as we come. And I guess I'll just mention that there's kind of a cool simulation approach that you can use when you're developing an optimization algorithm for sizing something like a thermal storage system, or a control algorithm for operating that system, or maybe you're trying to do both, right? So the idea there is that you have multiple levels of modeling fidelity. So you might have a simple model that's kind of they call it control-oriented or design-oriented model, which might be one of these low-order linear models. But then you have some deeper, richer model that has a lot of the nonlinear effects and a higher state dimension. Maybe it's a PDE model rather than an ODE model. So you can imagine using Modelica, for example, to do kind of a sophisticated, nonlinear, continuous model. And then you design your policy, or you make your design decisions or whatever based on the simple model, but then you simulate it in the rich, deeper, more accurate model. And so then you can check the robustness of whatever method you've come up with. Of course, the real test is then you eventually want to go and use it in the real world. And so then you want to put it on real equipment. And this is why I think kind of the control theory approach to design is kind of great, because those high fidelity models often end up having so many parameters that it's really hard to actually get them to accurately reflect reality. You can do it, but like it might take a year of a grad student's time, right? Whereas getting a simple model that's like, 80% accurate or something might only take a couple of days. So anyway, if your model is going to mismatch reality anyway, it's like, in my view, and I'm getting into personal opinions, this is not something that you have to believe or agree with, but I don't know, I think starting with a simple model and then just going directly to hardware often makes more sense than doing the intermediate kind of high fidelity simulation approach. That was a long answer to a short question. Does that make sense? Okay. Yep.
Okay, so, For the past VR to model the examples we've done on the homework groups, we have like, it's always like the single, like, within like single VR. So in the case where we have like combined multiple VR, so what happens do you think, we should go, I assume it's not just having the X and P's, there are some things like, what do you think, how should we approach it?
Yeah, so the question is, so like say I give you an exam problem that has, like the example I said, the battery inside the house, right? How should you approach a problem like that? How do you do the modeling step, basically? Because I haven't really shown you how to do that. So you'd need to, I think that would require a little bit more understanding of kind of the rationale for, say, the building model. Like we talked about thermal circuits and how they work and the analogies between, you know, temperature and voltage and power and current, sorry, thermal power and current. So then, you know, you might go back to that original modeling framework and say, okay, now I've got a heat source basically in the house. So this is just energy that's being dissipated into the house. And so that's, you could view that as kind of like the energy that comes off of my body or these lights or, you know, this laptop that's plugged in, right? It's kind of just another one of those. So then if you understand how those things enter into the building model, now you kind of get, you have an idea of how this new term, which comes from your other DER, the battery, how that would enter into the building model. Does that make sense? Kind of. Okay. Okay. It's a good question, a fair question. Yeah. Okay. Other questions? All right, so let's move on then and just, you know, rapid fire, talk about a couple of other DERs. So another one, a classic one, is refrigerators and freezers. So individually, these things only use typically a few hundred watts, but there are a ton of them, right? Basically, every home has a fridge, maybe a freezer too. So there's about 200 million of these things in the US. And each of them, you know, just like the air in this room or the temperature of the wall behind me, you know, there's some flexibility in its temperature. And it has some energy storage capacity, basically. So yeah, so they all have flexibility. And so you could imagine if you were a manufacturer of fridges, and I was a grid operator, and I said, hey, I really need load shifting flexibility. I really need you to be able to use less load during, you know, the peak times in the afternoon and use, maybe shift that load to the night or something. So you can imagine saying, okay, well, you know, I've got 1 million fridges out in the world, and yeah, that's fine. I can just cool them down a little bit, you know, in the late morning, so that rather than being 42 degrees inside, now they're 40 degrees Fahrenheit inside or something. Food doesn't care, right? The jug of milk in the fridge doesn't care. And the person who opens the fridge probably has no idea. Like, I can't tell you if, you know, some juice I drink is 40 or 42 Fahrenheit, right? So it's kind of, it's like, who cares? And each, you know, individually, that might only, you know, shift again, like on the order of 100 watts or something. But if you do it in 1 million fridges, then suddenly that's actually a really big resource, kind of on the scale of a nuclear power. So just running the numbers there, if we assume 500 watts each, and actually that might be a little bit high. Fridges and freezers are very efficient. And so maybe like 300 might be a better estimate. But anyway, you multiply by 200 and you get somewhere around 100 gigawatts of flexible capacity in the US. So for scale, a nuclear power plant is 1 gigawatt. And all of the electricity generation in the entire US is 1.3 terawatts, which is 1,300 gigawatts. So if we just look at the 100 gigawatts here from the fridges, it ends up being on the order of 10% of the entire US power grid. So it's like, it's not small. Individually, these things are kind of dumb and trivial, but together they are not that. So, and we can model these things using thermal circuits. And so basically the models look just like they do for buildings, for thermal storage, and so on. You could use a one capacitance model, a 1R1C model, where you have kind of the overall capacitance of all the food and the air and whatever inside the fridge is your C. And then you have an R that basically has to do with the insulation of the walls here. And you might have disturbance terms in there. So if I come and open the fridge, I'm letting a bunch of cold air out and a bunch of warm air in, right? So we probably wouldn't have disturbance terms, you know, like hot water withdrawals from a tank or something, but we would have these kind of random terms having to do with people opening the fridge or putting in, you know, hot stuff. Okay, so there's a class of things that people call deferrable loads, which is basically things that have deadlines, but flexibility in terms of when you, up to that deadline, when you run them. And then I was like, well, the only one I could actually think of as a concrete example was a dishwasher. So instead of saying there's a class of things called deferrable loads, I'm saying that dishwashers exist. So anyway, the idea here is that you want to run before a deadline. So for a dishwasher, concretely, it might be like, okay, you have dinner, you clean up, you load the dishwasher, by 8 p.m. or something. And then you don't really care when the dishes get cleaned. You just care that the next morning they're good to go. And so that gives you basically whatever this is, 10 hours of flexibility in terms of when you run the thing. And different dishwashers, take longer or shorter to run, but kind of on the order of 2, maybe 1 to 3 hours is typical. And they might draw somewhere between 1 and 2 kilowatts when they're running. So that's, let's see, again, running the numbers here, there's about 80 million dishwashers roughly in the US. It's about 110, 120 million homes, something like that. And that includes apartments and condos as well as, single family houses. But not all of them have a dishwasher. So, but I don't know, 70% or something do. So at 1.5 kilowatts each, when, if these things all ran at the same time, that would be 120 gigawatts of flexible capacity. So 120 nuclear power plants. So I don't know, can you guys think of any other devices that have that same pattern where it's like you just need it to be done sometime? Yeah, go ahead. Yeah, washer dryer. So I was gonna put that was the other thing I thought of, but then I was like, you know what, if I put my laundry into the washing machine at 8 p.m. say, like I need it to be done relatively soon so I can change it. And I don't want it to just like run and then leave my soggy clothes sitting in there for 10 hours, right? And then once I like take the soggy clothes and put them into the dryer, like I don't want to just leave them sitting there for 8 hours. I want it to run. But I don't know. Yeah, what do you guys think about that?
I think it still works. You just have more constraints. Like you wouldn't do it at night. You might start during the day.
Oh, that's fair. Yeah, I could say like, look, I'm gonna go out and run some errands. I would like the laundry to be ready to change by the time I get back. Yeah, so it could be over a time scale of 3 hours rather than 10 hours. Yeah, that's fair. Okay. Yeah. All right, so there's more than just dishwashers in this category. Anything else? I don't know. You guys can think of. I'm sure like in industrial setting, there's probably stuff like this where you're like, I need to smelt a bunch of aluminum, but I don't much care when I smelt it. Like it's got to happen between these times or whatever. Maybe. Okay, so we could say broadly, there's a category then called deferrable loads, I guess. Okay, and yeah, again, like people have published papers on this. They've done experiments with this kind of stuff. So if this is interesting to you, you want to include some stuff like this in your project, we can talk and find some resources for you. Wind turbines. So I think nobody has asked me this yet, but I think a natural question is like, why do we talk about solar and that's all, right? Why aren't we talking about other renewables or whatever? And you can find pictures of like they call them vertical axis wind turbines. So rather than looking like a big fan, they're flipped. And so they rotate like this, I guess. And you can find pictures of like those sitting on top of houses and stuff. So you can do it. But the issue basically is that, so yeah, the power output of a wind turbine scales with the cube of wind speed. And then wind speed increases pretty significantly with the height, basically above the ground. So there's a boundary layer at the ground, right? So there's a no slip condition, basically. So the speed of the air goes to 0 at the ground. And then as you get higher and higher up, it gets higher. So this is what the wind speed curve looks like. This is just a rough estimate. It's not real data, but it captures essentially the trend. And so the implication there is that basically the taller you can build your turbine, the more sort of economically viable it will be, because it's going to get basically more energy for, a given length of the blades, basically, because it's getting up into higher wind speed regions. And the flip side of that is that the little ones, they're cool, they're interesting. They can be good for some like off-grid type applications, but they're not very popular for use in cities and suburbs and stuff like that. Basically, the cost is too high. So I just like this. This is an example. I keep updating the slide. Like I teach an undergraduate class on thermodynamics, and we talk a little bit about basically conservation of mass and stuff like that. I talk about wind very briefly in that unit. And so each time I teach, I put a new picture in there because the world's biggest wind turbine is getting bigger and bigger, right? So like there's a new record set every few months or whatever. But this is the current one that I could find. So this is an offshore wind turbine with blades that are 130 meters in length. So the diameter of the swept area for this thing would be 260 meters. A Boeing 747 is 71 meters long. So this here, you could take two of the biggest planes I've ever been in and basically stack them nose to nose, and they would be just slightly longer than one of these blades. An aircraft carrier is about 300 meters long. So this thing here is like, yeah, a third, reaching almost a half of an aircraft carrier. So these are not small machines. They're some of the biggest machines that humans have ever built. This one is in the Strait of Taiwan, between China and Taiwan. And there's a wind farm there. I think it was built by a company called Three Gorges Energy, which has anyone heard of the Three Gorges Dam? A few people. Yeah, it's like the biggest hydropower facility and one of the biggest power plants in the world, maybe the biggest actually. I think Three Gorges, like there were three huge rivers that all got dammed. So I don't know what the power output is, but it's like 20 plus gigawatts, like 20 nuclear power plants, just from a gigantic dam, basically. Anyway, so that same company built, they do not build small things, I guess. So they built this offshore wind farm. Anyway, okay, so I wouldn't consider these DERs, right? This is not small stuff that we can coordinate many of. This is really a centralized power plant, I think. And then there's a bunch of things that use fuel that we haven't really talked about, except to say that they exist and can be used as backups and stuff like that. And they usually produce either heat or work, usually in the form of electricity. And so we've got various heating systems. We talked in the sizing of heat pumps unit. We talked a little bit about how you can size basically for cooling, and then you'll be too small for heating in a cold climate, but you can use some kind of backup. Often it's electric resistance, but it could be a wood stove, it could be a propane furnace or whatever. So, it could be powered by methane, aka natural gas, propane, heating oil, wood, various other things. Diesel generators are often used, especially in microgrids. Basically as some flexible capacity that can fill in, if the sun's not up and the wind's not blowing, you have some other power source. They can also be used to kind of regulate the voltage and the frequency on the grid to some degree. And then there's something called combined heat and power, and this actually is what Purdue does here on campus. So I'll show a picture of that in a sec. That's also called cogeneration. Co is with, right? So you're generating heat with power. Or trigeneration. Sometimes you'll have one plant that does, like Purdue's. It makes cold water used for cooling buildings, steam that's used for heating buildings, and then it also produces electricity. And then there are things that use fuel that don't actually burn stuff. So fuel cells are one great example of that. So a fuel cell is something that basically takes in, typically a hydrocarbon or hydrogen, and then just does chemical reactions to produce usually electricity, sometimes heat, sometimes both. So you might find these at data centers, right? Which is basically just warehouses full of computers. So one data center run by Google or something like that might have, I don't know, hundreds of thousands, something like that, of computers, the size of the processor in my laptop here. And if you just look at like 1 second, how much revenue, basically how much business flows through a giant data center like that, it might be in the millions of dollars. So downtime at a facility like that is just not tolerated at all. So they have redundancies on top of redundancies, both on the electrical side and also on the cooling side, because all those computers, they basically take in electricity and spit out heat. And so you need a lot of cooling to get rid of all that waste heat. So, so they will often have something like a fuel cell or a huge battery bank or both on site in case the power goes down, even for a second or two. Yeah, so these are useful again for backup, for maybe stability in microgrids and other purposes. And usually we can model these things with like a pretty simple equation, which basically says the fuel input times the efficiency is going to be equal to the output, whether it's the heat or the power or the sum of the two. It's not a perfect model. The efficiency, of course, is going to depend on various things, but this usually gets you, close enough to do some interesting work. So I will just wrap up then by giving a schematic of a combined heat and power plant. And this roughly is what the Wade utility plant on the south east corner of campus does. So this is I think, who has not heard of a Brayton cycle? You guys are all mechanical engineers. Are you not a mechanical engineer? You just forgot what a Brayton cycle is. Okay, cool. So a Brayton cycle is a gas power cycle. So basically the working fluid is typically air or some other gas, as opposed to a Rankine cycle where you have a liquid, typically undergoing phase change, right? So a vapor. Anyway, so how this works basically, so a fuel comes in, typically natural gas. You have some incoming air, runs through a compressor. You take that higher pressure air, mix it with fuel, light it on fire, and the pressure and the temperature go way up. And then you run it through a turbine, spins the blades around, and that produces shaft work. It makes the shaft spin. And then, that's connected to some magnets or something that are rotating through an electric field, and that produces electric power typically. And so that would be just a Rankine cycle by itself. You'd stop there and you'd say, okay, you're getting work out, you're putting fuel in. But now we have all this, hot, fairly high pressure gas coming out of the turbine. So you can do something with all that heat, run it through a heat exchanger and use it to warm up basically water. So it would actually boil water down here typically. And then you'd have steam coming into a second turbine, a lower pressure, lower temperature turbine. And that would produce another work output. And then from there you get, still some fairly hot steam, which you can run through another heat exchanger and warm up, basically condensate. This is just, kind of lukewarm water coming back from campus. You warm that up, maybe you can boil it, and you send hot water or steam back to campus and use that to heat buildings. And then it typically condenses the steam. So then you have water, circulates through a pump, and then back up here. So this whole thing operates kind of in a cycle. And actually at Purdue, we are not just producing the steam and the two work outputs, but we also produce you can imagine using the shafts to run a chiller or something like that to produce cold water as well. And so that gets circulated to the campus too. So if people are interested, we could go and take a tour of that plant. Who thinks that would be fun? Okay, looks like everybody. Who's already seen that plant? Has anybody already taken a tour of it? Well, so there's the Northwest Chiller plant, kind of by the COREC, and then there's the Wade utility plant on the southeast corner campus-ish. So you've been to the chiller plant, right? But not to the power plant? Okay, yeah, so we'll see. Okay, all right, okay, all right. Message received. I'll send an email. We'll see if we can set it up. Okay. All right, so we're just about at time, but any questions before we break for the day? Okay, let me just say then where we're going. So we kind of finished our modeling unit. This lecture hopefully kind of put a bow on it. And then from here, we're going to start talking about optimization. And we'll probably do maybe 4-ish, maybe 5 lectures on that. I was thinking we would get the optimization unit in before the midterm, but that probably won't happen. We probably won't finish it. We may, I don't know, we'll see how quickly we go. And then, so there'll be an optimization unit. And once we know optimization and we know modeling, we can start solving some cool problems. And so then we'll talk a little bit about control, but we'll also talk about, design and sizing type optimization of various DERs. We'll probably do a little bit of machine learning. Basically, if you want to predict something, like the water that people are going to use from, for showers, or the amount of solar that's going to get put into a battery or something like that. It helps to have at least a little bit of machine learning knowledge under your belt. So we won't go deep by any means, but we might spend a lecture or two on that. I don't know, we'll probably do a discussion lecture at some point. There's some material I'd like you guys to read, so it might feel like more like an English class for a class or two than engineering. I'm looking forward to that. And then, toward the end, we'll do project presentations. That'll be the last probably 2 weeks of class. We have a couple of guest lectures coming up after spring break. So anyway, I think the class will get a little bit more wide-ranging, and the format won't be so rigid and stuff like that after spring break. Okay, thank you all, and I'll see you on Thursday.